Welcome to this class. In this session, we are going to discuss about the Cramer's rule. Cramer's rule is a rule that was given by a mathematician called Gabriel Cramer, who formulated a method of solving a system of n linear equations in n variables using concept of determinants. So let's briefly introduce what the Cramer's rule means. And then we'll describe with a system of a 2 by 2, a system of two linear equations and two unknowns. So this method, this is a method that uses determinants to solve a system of n linear equations in n variables. So this is one of the conditions that it applies only when the number of equations is the same as the number of variables. And as we shall see, we must also have the determinant of the coefficients matrix to be non-zero for the method to work. It was this method was discovered by Gabriel Cramer, who lived from 1704 to 1752. So there's a brief introduction of the method. So let's illustrate so derivation of Cramer's rule. Actually, we'll pick just a simple case, a system of two linear equations in two variables. So we are going to derive Cramer's rule using a system of two linear equations in two variables, and then we generalize into a system with n equations in n variables. So consider the system of two linear equations in two variables, x1 and x2 given below. So this is a system a11 x1 plus a12 x2 equals to b1, a21 x1 plus a22 x2 equals to b2. Remember, this is the general way of writing a system of two linear equations in two variables, x1 and x2. So I want us to solve this system using elimination method to find the values of x1 and x2. So let's use elimination method to solve the system 1. Let's call this system 1. So the first thing I want us to start by eliminating x1. So step 1, elimination of the variable x1. So to eliminate x1 mean that now we have to generate similar coefficients for the first equation for x1 and similar with those for x1 in the second equation. So we can say multiply first equation by minus a21 and multiply second equation by positive a11, i.e. so I'm multiplying everything in the first equation by negative a21. So I'll have negative a21 a11 x1 minus a21 a12 x2 equals to negative a12 and then b1 a21, not a12, so because I'm multiplying by a21. And then the second one we multiply by a11, so we'll have a11 a21 x1 plus a11 a22 x2 equals to a11 b2. So that's what that instruction means. Then once we have this one, then we add these two equations. So add these two equations. So this plus this will actually give us 0 because minus a21 a11 is the same as is like term to a11 21. So adding and of different signs is a 0. So this will give us a11 a22 x2 minus a21 a12 x2 equals to a11 b2 minus a21 b1, i.e. ax2 is common, so we have a11 a22 minus a21 a12 x2 equals to a11 b2 minus a21 b1. Then which means x2 will be given by, so just divide through by this bracket, a11 b2 minus a21 b1 divided by a11 a22 minus a21 a12. So that is x2. And then for x1, similarly, we eliminate x2 by, so then now for x2 to be eliminated, so we have to say multiply equation 1, say by negative So for x2, I'll just write the equation. So we had a11 x1 plus a12 x2 equals to b1, and then 21 x1 plus a22 x2 equals to b2. So we want to find the solution for x1. So we'll multiply this one by positive a22 and multiply this equation by negative a12. So that will give us a22 a11 x1 plus a22 a12 x2 equals to a22 b1. This other one will give us negative a12 a21 x1 negative a12 a22 x2 equals to negative a12 b2. And then so we add these two equations. So adding this a22 a12 plus minus a12 a22, this gives 0. So this will give us a22 a11 x1 minus a12 a21 x1 equals to a22 b1 minus a12 b2. So which means a22 a11 minus a12 a21 x1 equals to a22 b1 minus a12 b2. And so if you solve for x1 will be given by a22 b1 minus a12 b2 over a22 a11 minus a12 a21. So this is the solution for x1. Let's call this solution for x2, call it call this one 2, and then let's call this one 3. So 3. From this one here, from 2, 2 which was giving us x2 to be a11 b2 minus a21 b1 over a11 a22 minus a12 a21. Then you see that this a11 b2 minus a21 b1, we can write this one as determinant of a11, then I write here a21, then b1 b2. This is how this the same as this, and the denominator a11 a22 minus A12, A21 is nothing but determinant of A11, A21, A12, A22. So which tells us that then we can say X2 is nothing but determinant of A11, B1, A21, B2 divided by determinant of A11, A12, A21, A22. And if you denote this one by A1, A2, just say this one, A2 over determinant of A, where A is the original coefficients matrix from the system. And from 3, remember 3 is where you have X1 is given by this quotient, A22B1 minus A12B2 over A11, A22 minus A12, A21. This numerator, A22B1 minus A12B2, the same as determinant of A1, so we're saying B1 saying B1, B1, B2, A12, A22, and A11, A22 minus A12, A21 is the determinant of A11, A12, A21, A22. So therefore, it tells you that X1 is simply the determinant of B1, B2, A12, A22 over determinant of A11, A12, A21, A22. You can say this one is given by A1 over determinant of A. So then now, from if you call this one 4, expressions for X2 in terms of determinants, and then this one 5, then there's something that is actually coming out from these two results. Remember the original, we had A11 X1 plus A12 X2 equals to B1, and A21 X1 plus A22 X2 equals to B2. And you see, if you write the matrix equation, we'll have A11, A12, A21, A22, X1, X2, which is given by B1, B2. And from 4, from above, X1 is given by determinant of B1. This is what you have found here. B1, A12, B2, A22 over determinant of A11, A12, A21, A22. And X2, we have determinant of A11, A21, B1, B2 over determinant of A11, A12, A21, A22. You see that there's a pattern here on how the solutions of the variables behave with these determinants. You see the original, this is our original coefficients matrix, this is a variable matrix, and then this is a constants matrix. So what's happening to solve for the first, remember this line corresponds to x1, this corresponds to x2. So to solve for the first unknown is simply is the determinant of a 2 by 2 determinant formed by replacing the first column by the constants vector, and then maintain the other column for the coefficients matrix, and then divide by the determinant of the coefficients matrix the way it was. Similarly, for the second variable, we have to have the determinant replace that place of second variable, the second column, by the constants variable, fix the first column to be the same as what we had in the original matrix A, and then divide by the determinant of the original matrix. And so this concept can be generalized for a case where we have a system of n variables, of n equations in n variables. So theorem, the Cramer's rule. So if a system of n linear equations in n variables has coefficients matrix with non-zero determinant. So remember, we are dividing by this determinant of the coefficients matrix, so it should be non-zero, with non-zero determinant then denoted by A, determinant of A, then the solution of the system is given by x1 is determinant A1 over determinant of A, x2 is determinant A2 over determinant of A, x3 is determinant A3 over determinant of A, all the way up to xn is determinant of an over determinant of A, where denotes the determinant of AI and the ith column of the matrix AI is the column of the constants in the system of equations. So that's what is a generalization of the Cramer's rule. So in the next session, I will demonstrate examples on how to apply the Cramer's rule to solve systems of linear equations. So thank you.